Yeah, so these are the results from the demonstration that we did in April on board the satellite. And what basically that we have as conclusions is that you can reduce the processing time, can compress data, and you can make it affordable. So here's the run that we did, and this is the raw data captured on the satellite. And what we're showing here is actually a highly compressed image, which we've upscaled back to put on a map. But the original resolution image never left the satellite. That remains there. And in fact, it got deleted after we did the run. So what we did on the satellite is instigate the computer to take an image from the camera. The location that it imaged was the northeastern part of Egypt, having the Sinai Peninsula, the entrance to the Suez Canal. And this is unprocessed. And the first thing that we did was sharpen the image, denoise, and remove a lot of the artifacts. So what you see on the left is the noise. And once a algorithm has a run over it, we're able to remove a lot of the background noise. And it's very visible in the water. On land, there's not that much noise that shows up. And this is usually the first step before you run any model or any algorithm on the data so that you're not picking up false positives. The second thing that we did after cleaning up the image is to filter out images that are taken in that pass, which are not of the Earth. So the satellite starts changing its orientation from pointing at space towards the Earth and then points away again. So there are a few images that you will have in that. If you take it as a folder, they'll have probably 10 images, and there's only one image that you really want. So we have a CNN that looks at each image and says, hey, not of the Earth, it's partial. Okay, this is completely off the target that we're looking at. Keep only this and delete the rest of them. So this is one model that ran on board. And this also relates to the use case that we spoke about, imaging the whole of a continent, but just prioritizing on the images that we really want. This is another pre-processing step that most folks in the geospatial field will be knowing, which is you do not want to run your algorithm on cloud pixels. They just introduce a lot of uncertainty, and many a time you really do not know if you're looking at vegetation up in the clouds or is it really on the Earth. So this is the first thing that gets done after filtering out the images. You do create a cloud mask, and this was generated on board in under a second. Now, once you've removed the cloud pixels, you also want to remove water pixels in case what you're looking at is to study the Earth. So reject all the water pixels. So run a water detector. By the way, just full disclosure, this image did not have near infrared. So without near infrared, it's pretty challenging to accurately detect water pixels. So we had to train a model that can do this. And it's done quite a good job, though because of the resolution, you really can't see the water pixels along the Nile River Delta. What you're seeing here is the vegetation on both sides of the Nile River. And the water pixels are there, but due to denoising, some of them get merged and you may not be able to pick that up. Now, with the cloud mask and a water mask, now you just get the land pixels that you want to run any vegetation classification. So we ran this to classify the land pixels into these three classes. So dense vegetation, sparse vegetation, and any other land use. So even cities and built-up areas would be the last class. So that's what gets run. Now, if you were to combine all the layers that we've generated, this is how it would look. And it's not that these were all generated as you see. These are all binary files that were generated on the satellite. Binary files, especially if they are nicely masked, are very, very highly compressible. So you can bring down the data size by 5 times. So imagine that. So it's a 100 MB file. What you're going to bring down is just 20 megabytes. So this is by putting all that information back together on Earth, we can sort of get this analytical view of an input satellite image. And we've placed this on a map as well. I can take you through this being hosted on Ellipsis Drive. So we've done georeferencing of the image. So it basically overlays perfectly on the base map. So what you see here is the upscaled RGB image with some warp, and on that you can superimpose each of the analytics that we have. So say the water layer, all that you would have brought down to the earth is just this layer, and it's very, very compressible. You can store that with a very, very small data footprint, and by hosting that on the platform, what you get is also you load only the pixels that you need. Now, if I were to bring the vegetation mask, now you can see the different classes being overlaid as well. So the intent of us doing edge computing is to, over time, reduce the dependence on the image itself. So imagine a future where satellites are generating just masks, vectors that you can overlay on satellite data processing systems or maps as is. So this really brings down the cost of both storage as well as compute. And it also, you can quantify statistically whatever is happening very, very quickly. You do not need to really interpret a multispectral image, as we see here. And we've also brought this into a data platform that we have. I can bring this up. So on this data platform, we allow folks to go through a time history of data collected over each location. And we've actually put the same image here. So you can view the water layer overlaid on the map. It's being pulled in from Ellipsis Drive. You can switch to the vegetation layer as well, which again gets overlaid perfectly on the base map. Yeah, so the usability of the data was actually something that we really wanted to answer. And even though it's being computed in a different way, it can be used exactly the same way as conventionally processed data on either the laptop or on the cloud.